use it. Okay, so Merman calls this Rule 2. Rule 1 was that unexciting rule that we talked about on Friday. And it tells us that in the normal way we observe a clock, of course, when the clock ticks off 1 minute, and we check that by any other clock, we're going to see that 1 minute of our time has elapsed. In other words, I feel like I've waited a minute when the clock on the wall ticks off 1 minute. That's the normal way we're used to experiencing clocks. When clocks are moving at a great speed with respect to us, or we're moving at a great speed with respect to them, in relativity, that means exactly the same thing. We have no experience with how clocks behave, and this is telling us that they behave in a rather counterintuitive way, in that if we watch a clock that is flying by us at a very high speed, and we check the time it takes it to tick off 1 minute, according to our own watches that we're carrying with us, and we feel like we're perfectly at rest as it's zooming by, we'll find out that it takes more than 1 minute to tick off 1 minute on that clock. And the effect gets more and more pronounced as the clock moves closer and closer to the speed of light. So what we're going to do first is sort of something that's pretty closely related to the derivation of the time dilation formula, that showing how it follows from the principle of relativity and the principle of the constancy of the speed of light. So those are going to be our starting points for all the relativistic effects we're going to talk about. And that derivation is not something you're going to be expected to reproduce on an exam. We need to, what I want you to know in this course is how to use the resulting formula, but still I want every step that we're making in the derivation to make logical sense to you and be understandable, even if I'm not expecting you to be able to put it all together to rederive that effect. Following that, I'm going to give some clarifying comments, because we're going to find out there are lots of ways to misunderstand this formula. So I will give 4 different clarifying comments that tell us how not to think about it, or additional things that we have to take into account when we're using that formula. And along the way, we will do a couple of worksheets. And then at the very end of the chapter, this will certainly be tomorrow, we'll talk about experimental evidence for time dilation. I mean, this sounds like something out of some sci-fi movie, but it's actually verified at particle accelerators around the world all the time. And we'll talk about a related kind of thing that involves muons being created in the upper atmosphere. Okay, so let's start out with the derivation of the formula. We've already seen the basis of it was something that we started out with doing on a worksheet. And then we continued it on the homework that you're working on now, working out some of the details that would come into play in this derivation. And the goal of that was to familiarize you with some of the arguments. So the idea is we're going to look at the ticking of a light clock. And we've already talked about the light clock having 2 mirrors like this. It's got a certain length like this. And this beam bounces back and forth. And we're going to consider one back and forth bounce to be 1 tick of the light clock. And we're going to have an observer who's observing it from the point of view, it's in this observer A is in the same inertial reference frame as the light clock itself. So the light clock is at rest with respect to this person. And of course, they're not going to see anything funny happening with the light clock. So here's what A is observing. A just sees that pulse going up and down. Of course, you might ask, well, how do they see the pulse? But we could have a little detector that beeps every time the light hits one of the mirrors or something like that. Things get interesting when we consider someone moving by that same light clock at a very high speed, a speed close to the speed of light. So here's a little space pod thing that happens to be zipping by in another inertial reference frame. We'll call that B, or Bob. And from B's point of view, since in A's, this is the picture according to A, B is moving, but in B's point of reference, they're thinking, I'm perfectly at rest. What's happening is this light clock and A are zooming by me. So let's redraw that picture from B's point of view. And in this animation, you can kind of see the essential point that why this clock is going to tick slower. The goal of today is to figure out exactly how much slower and how that depends on the speed. But since the speed of light, the principle of the constancy of the speed of light says these two pulses in these cases move at the same speed through space. It doesn't matter how you're moving, light always travels at the same speed. Well, this pulse has got to go on a much longer path. So of course it's at the same speed as the other one's traveling. Of course it's going to take longer to bounce up and down. And it travels on that triangular shaped or V-shaped path as opposed to straight up and down. Okay? So we're going to compare these, and we'll see, of course, what we've already concluded, that one is going to be slower than the other. And the question today is exactly how much slower. So just to define some terms, we're going to let t, this is the same notation as in the book, I believe. T is the time it takes one up and down tick, that amount of time, the time it takes in the clock's rest frame. And of course, that's going to be the normal amount of time that we would consider this to tick. Whereas in the frame where the clock is moving, this is the frame where we don't really have any experience in our everyday life, we'll call the time for one up and down tick as measured by a person in which the clock is moving like that to be t prime. And we're going to assume it moves at some speed v. We won't specify what v is at the outset. V can be something very small, 10 meters per second, but it could be close to the speed of light. We'll see that the formula we get doesn't make any sense for speeds greater than the speed of light, and we'll address that later on in the course. So just looking at simply the A picture over here. So from A's point of view, Alice, this light clock is at rest, and the distance in one tick that it has to travel is 2L if the length of the clock is L. And so just using, this is just distance equals speed times time, right? It has to go a distance of 2L. The speed is c, the speed of light. And so I could solve for the time it takes for one up-down tick as just 2L over c. Nothing profound, just lots of distance equals speed times time that we'll be using in this course to derive fx. Things get a little bit trickier when we go to B's point of view. From B's point of view, it feels like B is at rest, Bob, and he sees the clock zooming by in a different inertial reference frame. And these are the kinds of things that you considered, I believe, in the homework that's due today. Let's imagine that, again, the definition of t prime is the amount of time it takes to get from here to here. How much time elapses to get from there to there? If we only take half of this triangle, in other words, from this where the pulse is at the bottom to the point it reaches at the top, that's a time t prime over 2. And if the clock is moving at speed v, then this distance in space, that's what this arrow represents here. This distance in space is equal to the speed the clock is moving, v, times the time that's elapsed, according to the person who's observing the clock moving past them. And that time is going to be t prime over 2, because a full tick up and down takes time t prime. Okay, so that's this distance. Now, we worked hard on Friday, and here we're going to use the result that we got on Friday, that if this distance is L in the frame in which the clock is not moving, then when the clock moves in the manner we're showing here, this distance is still L. It's not shrinking along that direction. That's one reason why Merman bothers to prove that kind of uninteresting result first. It's being used in this derivation. So this is still L. And so I can use the good old Pythagorean theorem to figure out the length of the hypotenuse. In other words, what is this distance in space that the light pulse is traveling on? And it's the square root of L squared plus this thing squared, Vt prime over 2 squared. That's the Pythagorean theorem. So I've labeled that distance on the hypotenuse there. Now, we still haven't taken, in labeling the hypotenuse that way, we haven't taken into account the fact that there's only a fixed speed of light. Notice that c doesn't come into this formula at all. One way to take that into account, and that this was part of a homework problem that's, I believe, on the section 3 homework, but you should be working on it now, is to forget about that right triangle and just calculate this distance in a straightforward way, where we say, hey, if I want to calculate this distance, I can just use the speed that the object is traveling at times the time it takes. Speed it's traveling at is c along there, and the time it takes is t prime over 2 in this frame. So another way to calculate the length of that hypotenuse, but one that involves the constancy of the speed of light. In other words, it introduces a c in there, is to calculate it just by using distance equals the speed of light times the time that elapsed, which by definition is t prime over 2. So those two things are two different ways to measure the same hypotenuse, and so they're equal to each other. And our goal here is to solve for t prime. We're almost to the point where this is just an annoying algebra problem where we have to solve an equation for t prime. The only thing is the goal is to get t prime in terms of t, and right now there are no t's in this equation. But I can, because I can solve this relationship over here for L. Notice if 2L is equal to CT, then L is going to be equal to CT over 2, and I can replace that there in terms of L, and that will re-express that L in terms of T, and I'll have a relationship between T prime and T. I want to know if T prime is longer than T, so that will be the relationship that tells me how I can compare tick times for clocks in a frame where they're moving versus a frame where it's at rest. So we're going to make that replacement. L is equal to CT over 2. L is being squared, so the whole CT over 2 has to be squared. And now the rest of the derivation is just algebra. So we've done all the hard work. Now what we're going to do is take this most recent equation and say, hey, you're back in high school. You got to solve for t prime equals. And what do we do to solve for t prime equals? Well, generally, if one of your variables is stuck under a square root, the first thing you do is try to square it to get rid of the square root, because square roots are kind of annoying when you're doing algebra. So the first thing I'm going to do is, as always when you're doing algebra, you got to do the same thing to both sides. So if I want to square the left-hand side, I also have to square the right-hand side. So the next step, normally I would do this on the board, but because of the number of people at home, I think it's more straightforward to just do the derivation here on the slides. So having squared both sides, of course, the CT prime over 2 gets squared here. Oh, there's a typo there. This should be a T prime, I see. That's a typo. That should be a T prime right there. I just forgot the little prime. And then when I square the square root over here, that just makes the square root go away. So this is just what was under the square root. Okay, this should be a t prime there, and always when we're solving for a variable, if I want to solve for t prime equals, what I do is put all the variables on one side. In other words, collect together like terms. That's what you do when you're solving for a variable. So the first thing I'm going to do is, because there's a lot of stuff going on here, I'm just going to square out each term. CT over 2 all squared is the same thing as c squared times t squared over 2 squared. And similarly here, this is going to be a v squared times t prime squared over 2 squared. This will be a c times, it should be a t prime squared divided by 2 squared. And when I do that, of course, every one of the terms is going to have a 2 squared or a 4 in the denominator. And if I multiply both sides by 4, all those 2 squareds in the denominator will go away. And that's what the next step is showing here. I'm just trying to get all the garbage off of this. And now I'm in a point where there's not too much happening to the t primes here, so I'm going to go ahead and just put the t primes on the same side of the equation, and I can do that by subtracting this one off of both sides, and that makes it appear on the right-hand side with a minus sign. All right, I've got all the variables I want to solve for. I'm trying to get t prime equal, put them all on the right-hand side, and now when I've got these terms like this, we usually factor out the variables. So this is t prime squared times parentheses c squared minus v squared. That's called a factoring kind of problem. So here's the next step. If you distribute here, you'll see you get exactly the same thing we had before. So this is reverse distribution. That's the same thing as factoring. I'm trying to cover this in such a way that, even if algebra is far behind you, hopefully these ring some bells. And now I've only got one variable appearing. That was kind of my goal. The variable I want to solve for, t prime, is only here. And so my remaining goal is just to get all the stuff onto the other side and eventually take the square root to get t prime equals. The first thing I have to do is divide by this annoying thing that's multiplying t prime. When I divide both sides by it, it goes away from the t prime squared side, and it goes on to the other side. So on the other side, I have a c squared t squared over this thing. And then finally, I'm going to take the square root. I know it's not the most scintillating derivation. We were really done over here. We were ready, but we just wanted to put it in a nice form where we can see how t prime is related to t in a simple way. So let's take the square root of both sides. When I take the square root of the right-hand side, the square root of a ratio of two numbers is the same as the square root of the numerator divided by the square root of the denominator. So I just have a separate square root over each. And when I take the square root of the numerator, that just kills off the squares. So that's what happened there. The denominator keeps its square root on it. And now we're just going to do a last little bit of post-processing. We are almost there, but it will make this formula a little bit easier to understand, or at least it's a more standard way of presenting it, to get rid of this c in the numerator. And what we're going to do is do something that sounds a little bit strange to begin with. In the denominator, I didn't have a c squared in this term right here, but I can always multiply by c squared as long as I divide by c squared, right? If you multiply by a number and you divide by it, you haven't done anything to it, so there's no change in this case. The only reason I'm doing that is so I can get a common factor of c squared here. And so when I factor out that common factor of c squared, I would have c squared times 1 minus v squared over c squared. And then we can, well, that's what's shown here. And then we can use the property that if I have the square root of a product of things, that's equal to the product of the individual square roots. So that can be written as the square root of c squared times the square root of this thing in parentheses here. And then finally, I can cancel this c squared, square root of c squared, which is just a c, against this c up there. And that leaves us with the formula that we were after. It's called the time dilation formula. And it tells us, we'd have to do a lot of thinking about how to unpack this, but it tells us if a clock is moving by us at a very high speed v, that's what so whatever the speed the clock is moving by, it tells us I have to wait this long, according to my clocks, as I'm watching it move by, to have it tick off a certain amount of time. So if t is 1 minute, in order for that clock to change time by 1 minute, this is a formula that tells me how long I have to wait. And it may be 10 minutes to watch it just tick once. It just depends on what that speed v is. Okay, so clearing away all this kind of annoying algebraic stuff. Again, we're comparing the ticks measured to take time t in A's point of view to ticks measured to take time t prime from the point of view of someone who's watching this clock fly by at a very high speed. And we're finding that they're not equal. It's not telling us that t prime equals t. Newton believes that t prime equals t. Everyone believed that t prime is equal to t until Einstein published this paper in 1905. But this is telling us, well, we'll have to check out. Maybe when speeds are really slow, we'll see that t prime is really close to t. So you're not going to notice it when someone walks by with their wristwatch on at 5 meters per second or runs by at 5 meters per second relative to you. You're not going to notice it if they're moving at 1,000 meters per second. They have to be moving close to 3 times 10 to the 8th meters per second by you for it to become really noticeable. Okay, questions so far just on the derivation. Again, in this course, I want you to see all the logical steps. And if you see a step that doesn't make sense, call me out on it, and I'll try to explain it to the best of my ability. Some of it's just algebraic steps, but the most important part to me is that you come out of it knowing this formula and knowing how to use it. So that's what we're going to start practicing. Unfortunately, there's a lot of ways to misunderstand what it means, and that's part of the rest of our job today. Okay, so a moving clock is observed to run more slowly compared with a stationary clock. The first thing, so that's what it's saying, ticks take longer for a moving clock compared to when it's viewed from a point of view where it's stationary. And it could be the same clock or it could be a different clock. We're going to assume all clocks work exactly the same way. So it doesn't matter if it's the same clock being viewed 2 different ways or if it's 2 identical clocks and one of them happens to be moving and we're comparing to one that's at rest. There's no funny business where one of the clocks isn't working correctly. First thing to realize is that this formula only makes sense when v is less than c. Think about if v is equal to c, what would be happening in this formula? That's a no-no in your high school algebra days. we'd have a 0 in the denominator. We'd be dividing by 0, which sort of, some people might say is kind of like infinity, but at least it's ambiguous, and so the formula doesn't make any finite sense when v is equal to c. What about if v is greater than c? What would happen? It says this only makes sense if v is less than c. If v were greater than c, what would happen that causes problems? Well, what would, just in terms of mathematics, what would go wrong with the formula? That, yeah, we'd have a negative under the square root, right? Because if v were greater than c, this v squared over c squared would be a number bigger than 1. So when I subtract it off 1, I get something negative. When you take the square root of a negative, well, it's at least confusing. Maybe it's something imaginary, but even Einstein didn't have an idea of imaginary time being measured. Nobody really knows what that means. So this formula, in as confusing as it is, really doesn't make any sense when v is equal to c or greater than c. So it only makes sense when the clock is moving by us at a speed less than c. And we'll connect with that later on in the course and show that lots of things go haywire if you ever imagine that something is moving at a speed greater than c. Okay, this factor, what's multiplying the t here? What's multiplying t on the right-hand side is 1 over the square root of 1 minus v squared over c squared. That factor is so important, and we're going to see it appearing in several formulas that come up in relativity. It's given its own name, and that name is the Greek letter gamma. It looks a little bit strange in the font that I'm using there, but lowercase gamma, usually drawn like that. I'm drawing it big, hopefully, so the folks can see it without me switching cameras. Okay, and so what we're saying is, if v has to be less than c, what does that tell us about this whole factor that's multiplying t, that factor gamma? Gamma has to be bigger than or equal to 1. Notice that if v is very, very small compared to c, then this is a puny number there, right? If v is 10 meters per second and c is 3 times 10 to the 8th meters per second, this is just a super small number. And when I subtract it off 1, I get something that's really close to 1. And when we take the square root of something really close to 1, we still get something that's really close to 1. So when v is much, much less than c, this factor gamma is approximately 1 over 1. So it's very, very close to 1. But as v starts to get close to c, v over c is something that is, maybe a little bit less than 1. If you're going at 0.9 c, v over c would be 0.9. 0.9 squared is still a number that's pretty close to 1, right? 0.9 squared is going to be 0.81. When I subtract that from 1 minus 0.81, that's a small number, 0.2. And then when I take the square root of a small number, I still get a small number. You don't have to worry about the details of exactly what happens. But the denominator starts to get small. And when you divide by a small number, you make your ratio bigger, right? Dividing by a small number makes it bigger. And that means when v is very close to c, this gamma starts to get bigger and bigger, and it actually goes off to infinity. That's why we end up dividing by 0 when v goes to c, and we're not going to use the formula there. So here's a plot of, I know this is a little bit faded, they're hard to see, it's blurry, but this is supposed to be gamma on the vertical axis here. And this is v written in terms of c, right? So here's v equals 0. The clock's going by, the clock is at rest there. Here it's moving at a very slow speed. Here it's moving at half the speed of light with respect to you. And here is actually it moving at the speed of light. That's where we said we shouldn't use the formula. And it's telling us that gamma is almost 1 until you reach about half the speed of light. If gamma is 1, that means t prime is very close to t. And that means there's no time dilation effect. And that's exactly what Newton would believe. If you assess that 5 seconds have ticked off, everybody else, regardless of how they're moving, is going to assess that. That's what Newton believes. That's not true once you start to travel at speeds that are, greater than half the speed of light, certainly. All of a sudden, that factor gamma starts to get really big, and it shoots off up towards infinity as you get close to c. So gamma just gets larger and larger and larger without bound. So it can get as big as you want. The ratio of these two tick times can be as big as you like. Okay, so that means that clocks moving very close to C are observed to tick very slowly. The time it takes a clock to tick that's moving by you very quickly is going to be much longer compared to the corresponding clock when viewed at rest. It's going to be observed to tick slowly. But this curve is also showing us that a clock has to move very close to C for you to notice any difference. All the way up to C over 2, that's 1.5 times 10 to the 8th meters per second. That's a huge speed. We never see things going that fast, at least macroscopic objects. You know, you might say, well, I see light going that fast, but it's really hard to see light going that fast anyway. So normal objects don't travel this fast. And that means for most of the things, almost everything we're familiar with seeing, gamma is essentially 1. Okay, let's try a worksheet. This is, for those of you zooming in, this is one of the worksheets I attached for today in my email earlier today. So make sure you have that. If you didn't print it out, at least have it nearby and a piece of scratch paper so you can work on it. We're just going to work on the first 2 on this, and then we'll finish the rest of the worksheet shortly. But the first 2 just ask us to think about some numbers. And so get your work ready, and as soon as I pass these out to the class, I'm going to put those on Zoom into a breakout room so you guys can freely discuss the worksheet together. That would be a good time to turn on your camera so that you can have a real conversation with your classmates. Okay, we're just doing A and B for right now. And we'll get to the rest very shortly. Okay, so I'm going to put the Zoom people in a breakout room. I'm not used to using breakout rooms, so let's hope it all works wonderfully. And I'll pull you back when we're just about ready to discuss. One of the things that you need to know to do this worksheet is the numerical value of C in meters per second. Somebody shout that out for me. Otherwise, part A will be hopeless unless you're looking it up. Anybody remember the numerical value for C? Physicists remember it, but that doesn't mean the general populace does. Yes? Yes, and for all practical purposes in this course, we're just to save some memory space in our brain, we're just going to call it 3 times 10 to the 8th meters per second. It's just a hair under 3 times 10 to the 8th meters per second. So that's the value of C. And that's a number that on our Friday exam, you should remember, know that number. It's a huge number. If you're not familiar or if you're rusty with scientific notation, we can talk about that too. I'm assuming most people have seen times 10 to the 8th and knows that that means you put 8 zeros after the 3 if you want to put it in standard decimal notation. You know, 3 times 10 to the 6th is 6 million meters per second, so it's a factor of 100 bigger than that, 3 million meters per second. So 3 times 10 to the 8th is going to be 300 million meters per second. Stop me as I'm walking around if you have a question. This is a chance to try out your scientific calculator if that's gotten a little bit rusty. Make sure you know how to put big numbers into it. You could put it in standard notation, but you know, scientific calculator, it's much easier if you know how to put times 10 to the 8th in there without adding all the zeros on. You know, you could ask yourself, what would you do if it were 10 to the 32nd power? You'd be there all day. You'd probably make a typo putting all those zeros in. So it's much easier to do scientific notation. Okay. Too soon? Okay, so let's bring them back. I think we've had enough time. How's it going? Anybody having difficulty with their calculator? Difficulty with that 1 over the square root of 1 minus v squared over c squared? We're going to see that factor appearing over and over throughout the course. So that's something we've got to get really used to. And maybe what we will do is just do it together on the board now, because there are several incorrect ways you might interpret it. I'm just going to wait for... Okay, everybody's back in our room here. That's good. Okay, so let me go to the board. As Royce was saying, the answer to A is just, well, if we know the numerical value of C, then if we want 0.98 C, that's going to be 0.98 times 3 times 10 to the 8th meters per second. And the only question is whether you know how to put that in your calculator. A lot of times, scientific calculators, it depends which one you use. Like in my, people will often write this as 3E8, sort of in computer language or calculator language. That E usually means times 10 to the power. So this is 3 times 10 to the power 8. On my TI calculator, the way you put this in is 3, and then there's a button that has an EE on it, I think. You hit that EE button, and then you hit 8, and then you hit enter, and that would be 3 times 10 to the 8th. So I would do 0.98 times 3EE8, enter, and it would give me the result of that. And as Royce said, that's about 294 million meters per second. 294, if I write it in standard notation, just to make it look as amazing as it is, 294 million meters per second. Or we could write it as 2.94 times 10 to the 8th. Questions on A? And again, for you Zoom folks, if you have a question, just jump on in and shout it out, because you're on the room speakers. B, what's the value of the relativistic factor gamma for the ship in Earth's IRF? Okay, so here we got a ship that's moving relative to Earth. I didn't really read the statement of the problem. So gamma is equal to 1 over the square root of 1 minus v squared over c squared, or sometimes people will write it as v over c quantity squared. Well, notice if v is equal to 0.98c, then that means that v over c is just the pure number 0.98. And that's what we got to put in there for that square. So I'm just simplifying a little bit. I don't want to type 3 times 10 to the 8th in there if I don't have to. And in this case, v over c is just a nice simple number. So I'm going to put that in here. 1 over the square root of 1 minus 0.98 squared. Well, 1 minus 0.98 squared is still going to be close to 1, right? When you square a number that's just below 1, you get another number that's pretty close to 1. When you subtract that from 1, you're going to get a small number. When you take the square root of a small number, you're going to get another small number. So we're going to be dividing by something that's pretty small here. When you put it in your calculator, I get 5.025 is that gamma factor. So we'll call it close to 5, and that means for this particular clock at the speed it's going, as I watch that perfectly functioning clock go by at 0.98c, very close to the speed of light, if I look on my wristwatch and count off how many seconds it takes for the clock that's zooming by to tick off 1 second, I would have to wait 5 seconds for it to just tick off 1 second. So that's the one meaning of what it means to move slowly. Okay. Let's go back to these. Any other questions? Those are just mechanics kind of things, making sure you know how to compute that gamma. We're going to be using gamma a lot. Okay. Let's talk about one particular comment. I mean, here's something that people sometimes have a question about at the beginning. Wait a minute. If a clock ticks once per second, by definition, it's a perfectly well-functioning clock. How is it possible that either t or t prime would not be equal to 1 second? And so just to give a little bit of airtime to this, the idea is t and t prime are measurements of how long it takes a clock to elapse by a certain amount. So we're imagining this clock that we're observing is a new scientific experiment. And we're going to time with our wristwatch or whatever watch we have available and compare how long it takes a clock that's at rest with respect to us, that would be t, to tick once, versus how long a clock, that same identical clock that's moving by me at a fast speed, to tick the same amount of time, okay? And the point here is that when I'm looking at a clock that's at rest with respect to me, I have a lot of experience with that. That's when I look at the clock on the wall of the room right now. I'm used to looking at clocks that are at rest with respect to me. And it's no surprise that t, if t is 1 second, what that's telling me is that normally a clock, if it takes, if I watch it tick off 1 second and I watch my wristwatch, I would expect my wristwatch to tick off 1 second. It's almost by definition because we design all of our clocks the same way. That's the familiar context. How long I have to wait for a change in clock readings is, of course, by definition, the clock wouldn't be working correctly if it didn't read the amount of time I was expecting. Compare that to the point of view where there's a clock zooming by at a very large fraction of the speed of light. So here I'm saying, suppose 0.8c. Here's Einstein sitting here saying, well, wait a minute. If this clock is ticking off once per second, how long does Einstein have to wait in his own world to watch that clock tick off something? And that's an unfamiliar context. So we shouldn't suppose that we immediately know what the answer is. Newton supposed, and most people suppose, they do know what the answer is going to be. And that's called the idea of universal time, the sense that time elapses the same for everyone. We all march in lockstep, and 1 second is 1 second for everyone. Einstein saying that is not true. And that's what this T prime represents over here. How long this observer has to wait on his own watch to have this clock tick off a certain amount of time. And it doesn't matter if T is 1 minute, then T prime will be expressed in minutes because gamma is a pure number, right? If T is in seconds, T prime will be in seconds, and T prime will always be bigger than T, okay? Again, just to make the point that sometimes these clocks could be different clocks. We could be comparing a clock that's at rest in front of us to a different clock that's zooming by. Sometimes they'll be the same clock. In other words, we might want to say, well, how is this clock appearing to someone who's just at rest in front of it as opposed to someone who's zooming by? And the point is, it doesn't matter if they're the same clock or different clocks because we're going to assume all these clocks are identical. And they're all functioning the way any clock should. There's no problem with these clocks. We'll emphasize that again in just a second. Okay, so we're going to assume all clocks work normally, so it doesn't matter if they're the same or different. If they're different, physically different clocks, we'll assume they work exactly the same way. Okay, so let's finish up. I know some of you have gone ahead on worksheet 5.1, but finish up the other parts of this. I'm going to send the Zoom folks to a breakout room again, where you can think more about using this formula. You're going to need that formula in order to do the rest of the worksheet. Notice here at the top that it says a tick means a 1 second tick. So when I say how long does it take, we're talking about to tick off 1 second. I better take roll too. With my roll sheet. One, two, three, four, five, six, seven, 8, 9, 10, 11, 12, 13. Okay. How's it going? Anybody have any sticking points? C is supposed to be really easy, so sometimes I like to ask questions that seem absurdly simple because sometimes questions seem absurdly simple and they're not. But C actually is as simple as it sounds. It's one of those things we have lots of experience with, and it hardly even makes sense to ask it as a question because it seems so obvious to everyone. I'm trying to give you the amount of time so that most people in the room look like they're done writing, and most of you are still writing and calculating. F you might find to be a little bit challenging, so if you're stuck on F, I might stop us before you get done with it. But give it your best shot. Okay, so just to bring it back together, again, C is supposed to be, hey, something we have a lot of experience with. If I look at a clock on the wall and somebody asks me, how long from your point of view does it take the clock on the wall to tick off 1 second? That's the same as this question. They're looking at a clock that's moving along with them, or it's at rest with respect to them. And so if a tick takes 1 second, then of course they have to wait 1 second to see it tick off. That's the ship viewing the ship's clock. So it's the normal point of view. D asks something that is not like that. As measured from the Earth's inertial reference frame, how long does a tick of the ship's clock take? And that's exactly what this formula with the 1 over the square root, but I'm going to write it in the simple form because we already figured out that gamma was 5.025, and the formula for the time dilation says T prime equals gamma times T. Hey, that's a simple formula once we've calculated what gamma is. And so if the normal clock in its normal context takes 1 second to tick off, then we'll have to wait in a context where it's moving past us at a high speed, where gamma is 5.025, an amount of time which is 5.025 times 1 second. One S is 1 second. Okay, so 5.025 seconds is the amount of time we have to wait if we're watching it from the point of view of Earth as it's zipping by in the spaceship. Okay, jump in if you have a question on these. The formula there is not too complicated. We did all the work up above in B. As measured from the ship's inertial reference frame, how long does a tick of Earth's clock take? What do you think about that? Spencer?
Would it just be 1 over 5.5?
Well, no, in this case, it's actually not. Because, let me give Jack a chance to say he was raising his hand. What do you think about that? Yes. Right, so I'm on Earth. I see the ship coming by with a speed that corresponds to gamma equals 5.025. From the ship's point of view, they feel at rest, and they see the Earth zooming towards them with a gamma corresponding to 5.025. And so the situation is completely symmetric between the two. Now, Spencer's original answer says that we've got some explaining to do, because it seems like if my clock is running slowly, if your clock is running slowly, then from your point of view, my clock should be running quickly, and so we should have a factor of 1 over gamma rather than gamma multiplying it. And we do have quite a bit of explaining to do there, but for right now, we're just going to assert the fact that it's symmetric between the two. If I see you moving towards me at 20 meters per second, you see me moving towards you at 20 meters per second. And so the gamma factor is exactly the same for both of them. Each one sees the other one's clock is running slowly. And I know that sounds paradoxical right now. We've got a lot of explaining to do to get out of that apparent paradox. Okay, so the answer in E is 5.025 seconds, just like the answer in D. Now finally, F, this involves a tiny bit of algebra or arithmetic, I guess I'd really say. Suppose the ship is traveling by Earth at a different speed. Okay, it's not traveling by Earth at 0.98 c anymore. But suppose we want it to be the case that when the Earth looks at the ship's clock moving by as it flies by at this certain speed, they have to wait 2 seconds for a 1 second tick to tick off on the ship's clock. They have to physically sit there and wait twice as long in F. And so the answer in F is that we want gamma to be equal to 2. And so we've just got to figure out what speed, what fraction of c would give us gamma equal to 2. So let's write that out in a little bit more detail. Gamma, by definition, is 1 over the square root of 1 minus v over c squared. Okay, so we want that to be equal to 2. And I've just got to solve that for v, or v over c. It doesn't really matter. If we know v over c, then v over c is 0.7, then we would know v is 0.7c. So let's solve it for v over c. What would be the first thing you do algebraically? Again, because I don't know where everyone's at math-wise in here. We've got something stuck in a square root, in the denominator. So there's all sorts of bad stuff happening to the thing I'd like to solve for. Where would you start? What would you do? And everything we do, we got to do to both sides. Yeah. Yeah, so one thing you could do is take this thing in the denominator. I really wish my variable weren't in the denominator. So we could multiply in the numerator by this factor on both sides. So what's being suggested is we could multiply by the square root of 1 minus v over c squared. If I do it on that side, I've got to do it over here too. Square root of 1 minus v over c squared. Another way to think of it that I think is just a little bit simpler is you could just say, well, if the things in the denominator that I want, if two things are equal, their reciprocals are equal. To make sure I wasn't screen sharing. So if this thing, 1 over the thing we want is equal to 2, then the thing we want is equal to 1/2. Well, that's going to be what we get in a second here. But in this case, the whole point of doing that was so that these would cancel out like that. So we get 1 equals 2 times this, and that means that 1/2 is equal to the square root of 1 minus v over c squared. Okay, that was something. We're still kind of a long way from solving for what v is. What would you do next to solve for v or v over c? Square both sides. If you've got the thing you want inside a square root, you should try squaring. Okay, I'm running out of room over here, but I think the folks zooming in can see up here. So if I square 1/2, that gives me 1/4, right? 1 squared over 2 squared, which is 1/4. And that's equal to 1 minus v over c squared. And then I just want to get the variable that I'm solving for by itself. So what I could do is add it over onto this side and then subtract the 1/4 off on this side. You can tell me if this is confusing to you. V over c squared then is equal to 1 minus 1/4, which is 3/4, right? 4/4 minus 1/4 is 3/4. And then I'm going to take the square root of that because I'm looking for v over c. That tells me that v over c is equal to the square root of 3/4. And at this point, I can just go and put that in my calculator, which I did. And I get 0.866. 0.866. I realize I'm getting towards the end of the view of the camera, but I think you can still see that. And so that means v over c is this, so v is this times c. V is 0.866 times c. That's the answer I was looking for expressed that way. Notice that I never solved for v in meters per second and then figured out what a fraction of c it was because we already had v over c, and that doesn't involve me having to put a 3 times 10 to the 8th in my calculator at all. I really don't like doing those big scientific notation chores if I don't have to. Okay, anybody raise a hand or shout it out if you're on Zoom, if you have any questions about that. That's just practicing with the basic mechanics of this formula. Now, there's still a lot of subtleties that we've got to get into. We've got about 10 minutes left today, so let's talk about a few more comments that talk about ways that we might be misunderstanding what the formula is telling us. Okay. Comment 2 is, well, I've been talking as if one person is watching this clock go by, but it's not so simple. Here I say, observing that a moving clock runs slowly is just not as simple as glancing over your shoulder as the clock zooms by for one person to do it, taking a few readings and seeing, oh, I don't have to wait as long, even though it sounds like that's what we're doing. The problem is, when something's moving at close to the speed of light, even in a very short amount of time, it goes a huge distance away. And if it goes a huge distance away, if I'm trying to read what it says with my eyes, I have to wait for a long time for that light to get back to my eyes. Let me just illustrate that with a little kind of animation here. So here's a clock over here that reads 12 o'clock. And of course, it's going to be ticking up to 12:01, 12:02, 12:03. At this point, it reads 12 o'clock. Maybe it's really far away. Maybe it's close to the sun, or maybe even out of our solar system. At the time it reads 12 o'clock, here I am looking over here on the surface of Earth, watching to see what happens. The light from that 12 o'clock image leaves the clock, and notice, while it's traveling to my eye from a great distance away, this clock continues to tick over here. And so when that light reaches my eye right now, I think naively, hey, it's 12 o'clock at that distant location, if I'm not thinking very clearly. But it's not. It's actually 4 minutes after 12 at that location, at the time I'm seeing the image of the 12 o'clock light get to my eye. Right? Nothing especially profound there, except that the speed of light is finite. We don't even have to believe it's constant to see that there would be a problem there. So, for example, just to see how we might have some wrong observations, let's imagine someone on Earth is watching a clock go away at a very high speed. So this red clock is going to leave Earth, and I would like to know what time it is on, how much time has elapsed on this red clock, which is about to be moving away from us very quickly, compared to how much time elapses on the Earth clock. And let's watch what happens. Okay, so both are going to observe, because both these clocks are together on Earth. This one happens to be passing by, but right when it's passing by Earth, we say, hey, it reads 12, and the one on Earth that's going to stay with us reads 12, and now let's look what happens. As this clock that's moving away, and we're not worried about the light reaching the eye yet, we're just looking at the clock here. It's ticked off only 1 minute, whereas the Earth clock has ticked off 4 minutes. Why is that? Now it's clicked off 2 minutes, and the Earth clock is ticked off 8 minutes. That's the time dilation, right? We said that moving clocks are observed to run slowly. So Earth's clock is ticking off a lot more minutes compared to this clock right here. Okay, that's not the point of this problem that I'm pointing out here. That is the time dilation we're seeing there. All of a sudden, this clock reaches this other star, and we're going to be concerned about how much time elapsed on the Earth clock compared to how much time elapsed on the clock that was traveling to the star. Now, if I'm relying on light, the correct observation here should be the Earth clock read 1220 when the clock, in inertial reference frame B was at the star. It read 1205 when the Earth clock read 1220. That's what should be true. The problem is I can't see that right now, so I have to wait for that light to get back to me. So the image of the clock reading 1205 comes back. I have to wait. Meanwhile, the Earth clock's ticking off more and more. By the time the light reaches my eye, the Earth clock reaches 1240. And so the dubious observations, which aren't true, is that this person might naively say the Earth clock reads 1240 when clock B read 1205, when really it was only half that amount of time. They didn't take into account the fact the thing was, traveling at very close to the speed of light right here. Okay, so that's incorrect. Instead, to counteract that effect, we want to not just use one person sitting on Earth taking the observations, or one person glancing over their shoulder and watching as the clock goes by. Instead, we're going to imagine we have a whole army of people, all at rest with respect to the people on Earth, all with their clocks synchronized. Okay, so I've got a person who's on Earth, and I've also got a person on star X. And if I need it, I've got a person everywhere in between Earth and star X. We're all at rest with respect to each other, and our clocks are all synchronized. So I'm just going to draw that as a sort of big bar right here. We've got all these observers that are at rest with respect to each other. There's a clock on Earth. We'll call that, if that's IRFA, that's at rest with respect to the Earth and the star. And here I'm assuming the star and the Earth are at rest with respect to each other. There's a clock on Earth. We'll call that A1, and another observer A2, and their clocks are synchronized, and they're going to tick off in synchrony. Okay, and so let's assume that B moves at gamma equals 4. That corresponds to a certain speed that's very close to the speed of light. That would make gamma equal 4 relative to A. So that means in the time B's clock is going to be observed to tick off one minute, these two clocks should tick off 4 minutes. Okay, so they both record the correct things. A1 makes the record of what Earth's clock read when this one was passing by Earth on its way to the star. And then that starts going on the way to the star. Notice at every point, 4 times as much time has ticked off on the Earth clock as B's clock, and so on. When it gets to this star, notice that the correct observation we said is that when Earth clock, when this clock reads 12:05, the Earth clock reads 12:20. Well, the person on Earth can't see this clock over here. They would have to wait for the light to get back. So instead of having the Earth person take that observation, we're going to have observer A2, which is, a friend and fellow scientist of A1, but happens to live near this star. And they're going to be able to, their clocks are synchronized with each other. And this one's going to be able to observe that this clock read 12:05 when my clock read 12:20. No one has to wait for any light to get to them. And I already know my clock is synchronized with Earth's clock. And so I can infer that Earth's clock also read 12:20 there. Because, maybe we were light years apart or light minutes apart in this case. Okay, any questions about that subtlety? It's just really boils down to the fact that the speed of light is fast, but it's not infinitely fast. And so when things are moving at close to the speed of light, you might have to wait a while for that light to get back to you to see what happened. So even if you're watching something tick right as it passes you, it's not enough for one person to make the observations. You want to make sure you have, every time you're reading a reading on a clock, there should be someone right at the position of that clock in your reference frame watching it go by. The next tick, it's got to be someone down the line who's right there when it passes by, so there's no delay. It seems really extravagant, but that's, in principle, there's nothing wrong with it. Okay. And of course, that light comes back, but nobody's looking for that light anymore, so who cares? Okay, so we've made 2 comments so far. There's 2 to go, and we're not going to get to them today. So just to summarize what they were, comment 1 says, if a clock ticks once per second, how is it possible that we could not have either clock tick once per second? And the point is, they're measurements of how long someone has to wait for a clock to tick a certain amount of time. Of course, if it's at rest with respect to you, it behaves in the normal way. But we have no experience with clocks moving by us at large speeds. So t prime, if t is 1 second, there's no guarantee that t prime is going to be 1 second. We just don't have that experience. Comment 2, why is it wrong to just imagine one person watching it by and seeing how long it ticks? Is the problem that you're going to have to wait for that light to get back to you, and so you really can't be trusted. And so the point there is, we're going to have local observers using their local clock, and we'll have lots of people all at the same, in the same IRF, in other words, at rest with respect to each other, but still moving with respect to the thing that's flying by. Let me just finish with comment 3 because it's really quick, and then we'll start up with comment 4, which is substantial tomorrow. A lot of people, when they first see this, they say, well, look, you're just mistaken, or Einstein's mistaken, because that light clock is just a bad clock. Look, it's not working correctly. There's a reason we don't use light clocks, because we know light is funny. It travels at the same speed in all inertial reference frames. We know that causes crazy things to happen. So why would you ever build a clock based on ticks that are based on light travel times? Here's just a picture that we've already seen. Yeah, I mean, this clock can't be trusted. The objection is that that's just a bad clock. It doesn't run like a clock that we have on the wall or a digital wristwatch or something like that. The argument against that is that, well, we could place this light clock next to a perfectly standard clock, any other kind of clock, and we would see a certain correlation between ticks of the light clock. Maybe we have 1 million ticks of the light clock correspond to 1 second elapsing on this one, right? We could make those observations. And the idea is those events are going to correlate in exactly the same way. That's the principle of invariance of coincidences. If I observe that at this location in space, the light clock ticked off its 1 millionth tick at the same time the standard clock ticked off 1 second, then if I observe those 2 events being at the same location in the same time, then anyone moving at any other speed has to see them correlate. And so if I see 1 million light clock ticks or bounces for every second that ticks off on this clock, so is anyone else going to see that. And so if this clock is ticking slowly as seen by me, this clock also has to be ticking slowly as seen by me. It's a perfectly good clock because it will correlate exactly. So many up and down bounces per second ticked off on the standard clock. That's the principle of invariance of coincidences. a difficult phrase to say, but you also just need to think about that several times. I mean, there's a lot going on there. We're not used to thinking about the importance of the principle of invariance of coincidences. Perhaps most amazing, and our heart is kind of like a clock, right? It's beating with a fair regularity. Your cells, the speeds at which cellular processes are going on are certain kinds of clocks. The speed at which neurons are firing in your brain are certain kinds of clocks, right? Those are all things that happen at a certain rate. And if the light clock runs slowly, if we use the principle of invariance of coincidences, that means all other processes, including biological aging, movement, and so on. So if we imagine the fiction where one person could watch the ship going by at close to the speed of light, they would see the people moving really slowly. And if they could scan their brains, they would see the brain processing moving really slowly. And they would age less quickly than the counterparts on Earth who are getting more ticks of time go off, right? So the third comment is kind of short, but it's an easy objection to make and also an easy objection to shoot down as long as you understand the importance of the principle of invariance of coincidences. All clocks and movements correlate with light clocks, and therefore all movement is slowed when measured from an IRF in which it moves at close to the speed of light. Okay? And I'm going to put off doing worksheet 5.2 for one. Certainly, I haven't passed it out in class, so we'll be starting that tomorrow in the lecture and sort of doing the second half of chapter 5. We've got 2 more worksheets associated with chapter 5. This is a substantial chapter. Even though it's not long in Mermin, it's actually, there's a lot of ways to misunderstand what's going on in it. Any questions in the room before we go to office hours? Any questions on Zoom, folks? Yes, Jack. How about this? I'll just read it off rather than pass it out right now. Oops, wrong one. Observers in the sun's inertial reference frame watch a spaceship with crew travel from Earth to one of the sun's nearest star neighbors, Procyon, at a speed of 0.98 c. So someone's traveling to a nearby star at 0.98 c relative to Earth. Procyon has been measured by scientists to be so many light years away. So part of this is to think about what a light year means as a unit of distance, right? Light years just simply means the distance light travels in 1 year. And questions A and B are, as measured by observers and clocks in the sun's inertial reference frame, we're going to assume Earth and sun are all at rest with respect to each other. How long does the spaceship's trip to Procyon take? And as measured by observers in the sun's inertial reference frame, how long does it take for clocks on the spaceship to elapse by 1 year? If you want a copy, I'll give it to you, and you can think about it on your own. Anybody else who wants one is welcome to have it. Okay, so that's the end for today. If you want to talk about homework, any of the chapter 1 through 3 problems, the chapter 3 problems are the ones that are labeled 3.1 and 3.2. Hopefully that's clear. If you're on Zoom, if you want to hang out, I will try to pay attention to you guys too, and we can work out stuff on the board if you have homework questions. If you don't have questions and you're ready to turn in your homework, maybe you can just come and place them up here, stapled together in the way, in the order that they're listed.
Professor.
All right?
Professor.
Great. Yes, chapter 3 homework is due tomorrow, technically, and it's fine with me. It actually makes my life a little bit easier if you turn them all in together. I don't mind if the chapter 1 and 2 are a little late, but if you have questions on the chapter 1 and 2, and even chapter 3, I would suggest that you stay right now for a little bit and ask those questions, because it's going to be too much of a rush tomorrow. We don't want to put it off any longer because we're going to be finishing, hopefully, chapter 5 tomorrow. Chapter 5 homework is due Thursday to force you to do it before our exam on Friday. And I don't remember how many chapter 5 homework problems there are, but they're a little bit trickier maybe than the ones that were in chapters 1 through 3. Okay, Zoom folks, anybody have a question on the homework?
Professor,
Joyce?
Yeah, did you see that I emailed you my homework
I
last
did
night?
get your homework. Thank you. I haven't
Okay,
looked at
cool.
it yet, but I did receive it.
Cool. And then can the chapter 3 homework be due like with the chapter 5 homework on Thursday? Like you were saying that 1 and 2 could be due tomorrow with chapter 3?
I would prefer that you give me the chapter 3 homework tomorrow. I just, it doesn't hurt me at all if you let it go a little bit longer. As long as you've got it done, I don't care so much. What I don't want to do is to tempt you to not do it until Thursday, at which point you should be struggling with those chapter 5 problems.
Okay.
So if you have it done, certainly do turn it in tomorrow, and I really encourage everyone to do that just to keep you on task. When everyone gets it turned in, I can also post solutions and put them on the website. After I post the solutions, I'm not going to give credit for the homework anymore, and so I don't want to cut people out, but it is to your advantage to see my solutions and maybe compare a little bit with what you did. I'll try to get the homework when I receive it back fairly promptly, just because we do have an exam coming up. Okay, other questions? Just jump right in and feel free to leave if you don't have questions on the homework or any other office hour questions.
So just to be sure I'm going to turn in the right stuff. I did the chapters 1 and 2 homework that was assigned on 1013 and 1014, right?
Yes.
And that's what I was supposed to do, and I just I emailed this to you.
Yeah, email it to me, and I would actually prefer if there's some way you can put, you're taking photos of each page, I assume, since unless you
Well,
have a
I just
scanner at
wrote them.
home.
I wrote up my answers on a doc, and then I was going to
Oh,
send that
okay.
PDF in.
That's fine too. It would make my life a little bit easier if you could just turn it in with the chapter 3 tomorrow. So it won't be counted late, even though I have the due date as today.
Yeah.
Just so I minimize the number of files that I'm getting in email at any one
Yes, you don't get like 60. Yeah, I get it. Yeah. Okay.
Yeah. All right,
So,
thanks,
and we
Jacob.
don't have the solutions for these, right? Yeah, the solutions and reference items at the top there. That's for different worksheets, correct?
Solutions and yes, those are worksheets that we've done in class. And so
Yeah,
when we do a
not the
worksheet in
homework.
class, I try to post them after that day's lecture. So today I'll put that worksheet 5.1 up, and then after tomorrow you'll see worksheets 5.2 and 5.3 solutions go up.
Okay,
But
cool.
I will be posting homework solutions once I get the chapters 1 through 3 homework in from everybody who's intending to turn it in. I really do encourage you to get those things nailed down. We're sort of in a weird position where everything's going so fast. I don't feel like there's kind of enough to talk about before the first exam. The exams just come up really quickly, but I don't want us to wait too long and wait till we've done through chapter 7. Which is maybe how it was the last time I taught this course. So I'm going to rely on the fact that you've done these homework problems and you really understand them. So if you have any questions on the homework, think of that as your first line of defense for the kinds of things that you might see on the exam, things that are like what you did on the homework. So be very comfortable with those. That doesn't mean all of them, but I would say more than 50% should be very close to things that are on the homework. So if you don't know how to do the homework, you're going to be in trouble on the first exam. Okay, so lots of people are hanging out here. Somebody be bold and just raise their hand if they have a question. All right, Spencer?
Okay, so for 2.2, I suppose I was just getting a little tripped up on the part B where I wasn't quite sure like where to put, if the B was saying from time half or
Yes. Yeah, so this is very much like what we were doing today in class. Maybe the symbols are changed a little bit, so we got to make sure we have the symbols in the right place. But it's watching this light clock bounce as it's moving past us. Let's see, what was A? Express D in terms of V and TB. How are you on A?
I think I got it.
That's just distance it moves equals speed times time, right? So the time it takes to get from the first position to the second position is TB over 2. And the speed it's going at is V. That thing is moving. So it would be V times TB over 2. Okay, And then B says use the Pythagorean theorem and your answer from part A to express the diagonal distance, the ball. This is a ball. It's not a light thing. I guess it is a ball. We're thinking of it as a ball here, but we're going to treat our light clock kind of the same way. What do we know about the speed of the ball? Let me just make sure I understand what we're talking about here. Okay, so this thing is moving by us at a great speed. It is a light pulse. I'm not sure what the ball means. There's no ball, there's a light pulse. When it says ball, that's just a typo by me. It should say the light pulse, not the ball. Otherwise, we wouldn't know what the speed of the ball bounce was from the information that's given. So in B, we've got a picture that looks like this. Here's the light pulse going along that diagonal distance pictured. This distance is labeled as D, but we've now, by virtue of part A, been able to write it as the speed that the light clock is moving at. And I tend to write my V's with little tails on them as if they're script V's, but that's a V, times the time that elapses between these two times in the B frame in which the clock is seen moving. And that's half a tick. So that's TB, if T is the time of a tick, divided by 2, because it's only gone a half tick by the time it reaches there. And this, we now know by our work on Friday, if it was L when the thing was at rest, it remains L when it's zooming by us because it's a perpendicular dimension. So it's not going to shrink as observed by us along that direction. And so the Pythagorean theorem is just saying this distance right here is going to be the square root of this squared VTB over 2 squared plus this squared, L squared. Okay, let's check and see if we've done it correctly. It says express it in terms of TB, V, and L. Yeah, those are the only variables in there. So it looks like I'm successful in having done that. And that was just like what we did in the first part of making that equation that we were so concerned about today. Okay, C then says, concern yourself with that same diagonal, but now forget about using the Pythagorean theorem. We're not even going to look at these. We're just going to say, I can calculate that length because I know that there's this beam of light going along here. And it goes for a time TB over 2, and it goes at a speed c. So this same diagonal distance can be written as the speed that this thing is moving at times the time it takes, TB over 2. So that would be the answer to part C, this part. And then after that, we're supposed to equate your expressions from B and C. That's the equality I've written here. And solve the equation for TB in terms of the other variables. And that's a little bit of algebra. I don't know if I hit your question in there, Spencer.
Yeah, I think I was just getting confused with some of the placeholders and stuff like that.
Yeah, you know, a lot of times when people aren't used to doing physics kinds of math problems, it's a little bit confusing when you see an algebraic expression with 4 variable names in it. And you just got to be comfortable with just saying, I don't even know what those are, but I know when I multiply it by 2, it's, you know, it's the same as if there were a number that I had there. That takes a little bit of getting used to. Other questions? Everett, do you still have one? 3.2. Let's see where my problem 3 stuff is. Oh, chapter 2 and 3 homework. It's the same homework set. Let's see. 3.2. Hey, this is something we're going to see appearing. Again, this is foreshadowing and help us think about a derivation that's going to happen in the next chapter, chapter 6, having to do with the length contraction. Now, there are A through G parts to it. Is there any one part you want to start on? It would be easier for me if you turned it in with the stuff tomorrow. So if that's okay with you guys, just don't lose it between now and then. It will just give me less papers to hold on to. Sure. The entire problem. Okay, so maybe if we start it, you'll sort of get the idea in the first few. So in this case, we got is it a light clock? Yeah, it's a light clock. Just instead of pulsing this way as it's moving by us. It's pulsing back and forth along the same direction it's moving, which is a little bit more complicated because as it leaves the back of the bus and it starts going towards the front of the bus is moving, but of course it's going pretty fast, so it's going to catch up with it eventually. And so we're just supposed to kind of read it one step at a time, and hopefully I'm going to lead you through it in a way that helps when we see the derivation in chapter 6. Okay, so we're told that the length of the clock is a distance L. And I think that's supposed to be, I haven't read the whole problem again, but that L is a distance as measured in this frame where the clock is moving. Okay, and we're going to find out that's different than the length it has when it's at rest. But as it's moving by us, we see the distance between the mirrors as being distance L. And the clock itself is moving along at speed V. All right, and let's just start reading these. By focusing on the pulse's movement between the first two images. Okay, so this is the time it takes the light pulse to leave the back of the bus and travel to the front of the bus as the front of the bus is moving away from it. Calculate the distance d0, how far that light pulse has to travel as it moves from the back to the front, as seen by a person who's watching this go by. In terms of c and t0. Well, T0 here is what? I've got to read the text here. It takes time T0 to get from the back wall to the front wall. So if observed by me, to get from there to there takes time T0. And it's moving at speed c, so I can use distance equals speed times time to get the fact in A that D0 is equal to c times T0. Okay, good. By focusing on the rod's movement between the first two images, calculate the distance d0 in terms of v, l, and t0. v, l, and t0. So we're just going to say, how could I calculate d0 by adding a bunch of things together? Well, how far did that light pulse have to go? It had to go from the back of the bus to the front of where the front of the bus was, plus how far the front of the bus moved. So we're just going to add those two things together, right? It had to move a distance L plus however far the front of the bus moved while it was in transit, right? And the distance it moves while it's in transit is the speed the bus is moving at times the time that has elapsed. So some of these things are just, they're so simple, but if you don't look at it the right way, it's like, what? But we're adding, we're just saying, look, let's add together. It has to move this length plus the extra distance that the front moved, and I'm going to calculate the distance the front moved from speed times time. And in between those first two images, time t0 elapses again. So that's how far the front of the bus moves, and this is the length of the bus. That's how far it had to go. Okay. Again, I've calculated two distances two different ways. I'm going to set these equal, and we're told to solve for t0, right? If I set these two things equal, you can probably solve for t0. That's the idea in A through C. Now, once you've done that, look at the time between the second image and the third image, and you're going to do the same thing, except that it's slightly more complicated because instead of heading towards the front of the bus while the front of the bus is moving away from me, now I'm heading towards the back of the bus and the back of the bus is moving toward me. But it's the same kind of logic that we're going to do to get a second equation that relates those two. Yes? And you're agreeing with these two expressions here? I'm just going to end this so I don't record